Hi, welcome to our third lesson on eigenvalues and eigenvectors. If you haven't looked at the previous two lessons, can I suggest that you do that first before encountering on this one, otherwise you may miss some of the ideas that we discuss. Now, we're going to take a slightly different approach this time. I'm going to give you three different transformation matrices, and hopefully you can recognize what these transformation matrices represent. Okay, they are all reflections. The first one tells us that we've got a reflection in the x-axis. The second one tells us we've got a reflection in the y-axis, and the third one is a reflection in the line y equals x. Okay, so we've got a reflection in x-axis, and then we've got a reflection in the y-axis, and then we've got a reflection in the line y equals x. Right. Okay, so now rather than algebraically looking at these, we're just going to see if we can decide what the eigenvalues and eigenvectors are going to be of this, and then we're going to see if there's anything that we can get from that. So first of all, we'll look at the determinant first of all. So the determinant for each of these, well, that times that, take away that times that's going to give me negative 1. And let's just think about what that's saying. That's saying that I've got reflection in the x-axis. So let's see if we were looking at this particular shape here. And if I reflected this in the x-axis, my shape's going to end up down here. Now the area of that hasn't changed. The area hasn't changed, but because it's kind of been flipped over, that's the way I like to think about it, then the area becomes negative. Well, it's a directed area, we could think of it that way. So although the area hasn't changed, the direction of the area has changed, and that's why we get a negative in our determinant. So this is a negative 1, and that tells us, the negative tells us it's a reflection, and the 1 tells us that the area of it hasn't changed. Okay, similarly over here, a reflection in the y-axis would have the same effect, so we would expect the determinant to be negative 1 for that, which it is. And over here as well, a reflection in the line y equals x, again I would expect the determinant to be negative 1, which it is. Okay, so now looking at the first scenario, my eigenvalues, well, along here I've got a line of invariant points. Each of these points along this mirror line here are going to map back onto themselves. So that tells me that one of my eigenvalues has to be 1. My other eigenvalue, so if I look along the y-axis here, then my other eigenvalue is telling me, well, that point there is kind of being stretched in a negative direction by a factor of 1 to that point there. That point there is being stretched in a negative direction to that point there. So that tells me that I'm going to have an eigenvalue of negative 1. Well, the eigenvector for the first one is going to be 1, 0, because that's the direction of our x-axis. So my eigenvector 1 is going to be 1, 0, and the eigenvector for the eigenvalue negative 1, well, that's going to be this line here, so that's going to be 0, 1, yeah, or any multiple of 0, 1. Right, similarly down here, well, if it was a reflection in the y-axis, well, let me just move that over here. Okay, this time our y-axis is going to be our invariant line of points. Every point along the y-axis is going to map back onto itself, and this here is going to be our invariant line that's going to have an eigenvalue of -1. So I'll write them in the same order again. So I've got an invariant line, a line of invariant points and an invariant line here. So my first eigenvector, or the line of invariant points, which is this one here, is going to be 0, 1, and my second eigenvector is going to be 1, 0. Okay, finally we have got our reflection in the line y equals x. So if I just draw in the line y equals x for us, we'll have a red line. Whoa. Okay, so along this line, I'll just get rid of this, we can see that we're going to have a line of invariant points. Anything on the mirror line is going to have an eigenvalue, it's going to map back onto itself. So this has got an eigenvalue of 1, and then we're also going to have an invariant line that in this direction, so that's going to have, because everything's going to kind of map the same distance away from the line on the other side, that's going to have an eigenvalue of -1. So we're going to have that again, and this time our invariant line is going to be 1, 1, and this direction here is going to be -1, 1, and there you go. Right, the key thing to realise here is that every pair of eigenvalues that we've got here, here and here are all the same. We've got an eigenvalue of 1 in each of them, and the other eigenvalue is -1 in each of them, and this is always going to represent a reflection, and also our determinant is always going to be -1, and also our eigenvectors here are always going to be perpendicular to each other. Yeah, so the one corresponding to the one will tell us our reflection line, and obviously the lines that the points that reflect will reflect perpendicularly to the reflection line. We can do a quick check, and the dot product of each of these should be 0, and that shows that they're perpendicular to each other. Right, what we're going to do now is we're going to get a quick overview of the transformations that we've looked at. When we had two different eigenvalues, A and B, we decided that that's going to give us a two-way stretch, like so, where in this particular case the x-axis and the y-axis are our invariant lines. I've been careful here to say that this is when A is not equal to B. If A is equal to B, then we've got an enlargement, and in fact every single line that goes to the origin would be invariant in that case. If the eigenvalue is, if we've got a single eigenvalue that's 1, then that's telling us that that's going to be a shear, and so that's going to be something that looks like that, and we've got a line of invariant points, which is the axis along which the shear is taking place. So in this case it's going to be the x-axis. And finally we looked at a reflection, and it's kind of a special case of a two-way stretch where the eigenvalue is 1 and -1, so we've got an invariant line of points, and and then we've got this invariant line that gives us this reflection like so. Right. One of the things, well, a couple of things to point out. First of all, that we could have situations where we've got a combination of these. So, for example, I could have a shear like so, followed by a stretch. So that would give me a single eigenvalue of say 2, for example, which would mean that it's shared and then stretched by a factor of 2. Or I could get a reflection followed by a stretch, etc. The other thing that could happen is that I don't get any eigenvalues at all, so I get no real eigenvalues, I should say, because eigenvalues could be complex, which is something that you may look at university if you go on to study that far. So I could have no real eigenvalues, so that would tell me that that it may be a much more complicated transformation that involves some sort of rotation, etc. And the final thing that I want to go on to say is that we are only finding invariant lines using this approach, or lines of invariant points that are going through the origin. There may be other invariant lines that don't go through the origin, and there is actually a different approach that we can use to find those. So, for example, on the shear, we've got a line of invariant points that goes through the origin here, but we haven't got any invariant lines that go, other invariant lines that go through the origin. But you may be able to spot that there's lots of invariant lines here that don't go through the origin. So, for example, this point here maps further along this line here over here. Similarly with the reflection, I've got my line of invariant points here, and I've got another invariant line that goes through the origin here, but actually anything parallel to that is also going to be an invariant line, and that's something that we can't find using our eigenvector approach. Okay, thanks very much for joining me for this, and if you've got any questions, feel free to let me know. Otherwise, I will see you again soon.